Okay. All right. So let's recap. Let's recap some of our Lego pieces. So one of the first, well, not the first, I would say, but one of the Lego pieces that will be definitely required in today's class is going to be a multiplexer. So here I'm showing you a 2x1 multiplexer. The definition of 2x1 multiplexer is as follows. There are two lines that are contending to come out the other side of the multiplexer. For example, in our previous class, I had put Gafur versus Ramesh together, right? So these were contending together, contending against each other to sit on the chair. Now, what the multiplexer does is it has a select signal. If you have a 2x1 multiplexer, that select signal has to be just one bit, because that one bit can be either a 0, in which case, let's say Ramesh will be allowed to sit on the chair. If it is 1, in which case Gafur will be allowed to sit on that chair. Now, depending on type of application, you may need to use a bigger multiplexer. For example, a 4x1 multiplexer, meaning that there are four lines that are contending to come the other side of the multiplexer. So my question to you is as follows. How many select lines would you need for 4x1 multiplexer? How many bits do you need to allow one of those 4 lines to pass through? Discuss, have a chat, and tell me. In 2x1 multiplexer, we have 2 contenders, and you only need 1 bit, because that 1 bit can be 0, allowing A to pass through, or it can be 1, allowing B to pass through. However, if I were to give you 4 lines, how many selection bits would you require? 2. 2. Arcos, do you agree 2? Right? I'm sorry, say again. The 2 bits will allow one of the 4 options, right? Okay. Okay. Sorry. All right. So you would need 2 bits, right? You would need 2 bits. 0, 0, A goes through. 0, 1, B goes through. 1, 0, C goes through. 1, 1, D will pass through. If it is an 8x1 mux, how many selection bits would you need? 3, exactly. So if you have n selection lines, if you have n contenders, the number of selection bits that you would require is log to the base 2n, right? Log to the base 2n if you have n contenders. Some other pieces that we have seen so far, which we will actively use in building our data path, is your ALU. Now, ALU is a bigger unit than a simple adder, because ALU, depending on the operation, depending on the R-type operation, it will be doing a lot of things. It can do addition, it can do subtraction, it can do XOR, it can do XNOR, which we are not considering. It may also do shift left logic and shift right logic, which it will be doing in our assignments. So the ALU is going to have the ALU result. Additionally, it's also going to signal a 0 flag. That 0 flag will be used to decide whether to branch on equal or not. Then we have seen the instruction memory, where your instruction is stored, your register file, that's quite important, program counter, which holds the address of the next instruction. So the program counter value goes into the instruction memory in the form of an address, and from that address, an instruction is fetched. Then the data memory. Now, if you are looking into load and store word instructions, you would need the data memory, because when you are using load and store word instructions, when you are using the load word instruction, you're loading the value from the memory into the registers. And this is where your data is coming from, this data memory file. If you're using store word, you're storing a value from the register into the data memory. So all of these 3, register memory, instruction memory, and data memory, they're all distinct items. You would require an adder and, of course, a clock pulse, which will be implicit in our design. Okay. So far, we have seen how to design our instruction fetch memory, which is right here, Right now, technically, it's not very important for it to occupy the entire real estate on this slide. So it's a little bit cut off, which we will not worry about. Now, what I would like for you to do is discuss with your peers and think how we can create our load word hardware. Now, this is how the load word hardware works. The first operand is going to be the RT register. The first operand is going to be the RT register, which happens to be bits 20 to 16. So when the instruction comes out, the bits 20 to 16, that's going to be the RT register. In the parentheses that you see, that's your RS register, which will always be the instruction 25 to 21. So whatever instruction is coming out, the bits 25 to 21, those are going to constitute the RS register. RD is, I guess, in this case, 15 to 11. I don't know whether you would require RD or not. Do you see RD in load word? No, perhaps we don't require. 16 there is your immediate value, which is 15 down to 0. What I would like for you to do is discuss how this load word hardware is going to function. Now remember, this is how the load word actually works. In this case, we are doing load word $S0 $16 SP. This is what the hardware has to do. Hardware has to use the ALU to compute the address. So this is going to be the address, 16 plus $SP. Now this address will be used by the data memory, which will spit out the value which is at that address. And that value has to be returned to RT. Right? This is how your load word works. This is RT, this is RS. What your hardware has to do is it needs to compute the address, which is 16 plus $SP. In this case, $SP is RS register. And the address that is generated, it is sent to the data memory, and that is going to spit a value, which will be written to the RT register. Now, using your Lego pieces, please make the appropriate connections. First, think about it on your own for the first 5 minutes. And then for the next 5 minutes, brainstorm, engineer with your fellow computer architects how you would join these Lego pieces together to accomplish load word instruction.
I think so, yeah. I think immediate will go to A. And the result will go to others. And RC will go to write data. RC is the result. It will go to our so yes, because RC is where to store. So you don't really take data from RC. You put data to RC now. Oh. So if you put RC to the register, what are you going to do? RD. Yes, exactly. But so is it delivered? Okay. This is the answer. Immediate plus RS value. RS goes to register.
Now, please actively have a chat with your peers. Brainstorm. Make some noise.
So yeah, so that's if you go. This is the standard.
So, for example, for load word, first we have compute
So ALU.
where we want X to Y. So 16 plus $SP would actually be your address, right? So you need to compute that address. And as it so happens, 16 is the immediate value, which is 15 down to 0, and $SP is the RS register, right? So ALU has two inputs. One of them has to be the RS register, and the other one has to be the unit, right? Now, where would you feed the RS register so that the read data one comes out as the RS value? So not just yet. First we need to basically read the value, right? So ALU has two inputs, right? You see one input is coming from read data, and other data is still undecided. Now, we know that in order to we need to do immediate plus the RS value, right? Let's talk about the RS register. Where would you feed the RS register on the left side so that read data one comes out as the RS value? But not quite yet, but you will connect the RS to read the 0. Well, typically it's not quite done yet. The pieces are not very broken.
So
Right, the arrow is not all the way to the read register one. Okay, so RS value will come out. What about the
It's gonna be data.
second operand of
Right,
the
data,
one with
right.
the tiny line?
Oh,
That
address. Address.
not quite read data two, because when you are doing read data two, you're reading off of the register file. You're reading the register value. But we need to perform immediate plus RS value. That's going to be immediate, right? It's not going to come from the register. Because if you want to operate on two registers, then both of them will come from read data one and read data two. But since here one of the operands is immediate, that has to come from that line.
Oh, address goes the.
Right? Okay. So that will be fed to address, and think what will happen next. Once you get the data, you the register, write it in the RS. Very good. Awesome.
Okay, excellent, excellent. Now, are you ready to see the solution? Now, one thing that you have to remember here is read register 1, read register 2, and write register. These are 5-bit codes. The reason why they are 5-bit codes is because they are expecting either RS, RT, or RD, which will specify which register to read in the case of read register 1 and read register 2, and which register to write into in the case of write register. Write data is going to get a 32-bit value. Data is always going to be 32-bit value because we are dealing with MIPS 32 bits, right? So this is what is going to happen. We want our ALU to do this immediate plus the RS value. Now, if you take a look into the ALU inputs, it has two inputs. One is the read data 1, and the other one is read data 2. So what I can do is, if I were to feed RS into read register 1, then the RS value will come out, right? Similarly, if I were to feed immediate 15 down to 0 to this second ALU input, my ALU would produce RS value plus immediate value. So this is what is going to happen. I'm going to bring those Lego pieces together. So RS goes into read register 1. RS goes into read register 1. Immediate value goes to the ALU. There's one special thing that is going to happen to immediate value. Some of you may not have seen this, but it's okay. The sign extension. The reason why we need to perform a sign extension is because ALU works on 32-bit values. So let me repeat this one more time. The reason why we need a sign extender or a sign extension here is because the ALU works on 32-bit values. Our immediate value is 16-bit. The read data 1 that is coming out is actually 32-bit. So there's a bit mismatch. We don't want that mismatch to happen for our ALU. So what we do, we extend the immediate 15 down to 0 to become 32 bits. Essentially what you have done here is the 15th bit, 0, 1, 2, 3, all the way to 15th bit, that is just replicated using zfill or something, right? You're filling it for 16 times. And therefore, you're doing a sign extension. Now, what I would like for you to do is think about this. Why would you need a sign extension? There are two reasons. One reason I have given you, and that is to make it a 32-bit value. But why sign extension? For example, if the 15th bit is 1, then I'll fill 16 ones in front of it, making it a 32-bit value. If the 15th bit is 0, I'll fill it with 16 zeros to make it a 32-bit value. Why not just zero pad it? Why have to extend the sign? Very nice, because 2's complement is going to come into place at a certain point. Your load word instruction, the immediate value can also be negative. It can also be negative. If I were to zero pad it, then I would have destroyed the sign. I don't want that. Therefore, in order to preserve the 2's complement, in order to preserve the sign of the number, I need to sign extend it. Now, here's the definition of sign extension. Please note it down. Sign extension means sign extension is replicating bit number 15 for 16 times to make it a 32-bit value. That's what sign extension is. Sign extension is very different than what we have, which is called as zero padding. I'll talk about zero padding later. Sign extension is to replicate the 15th bit for 16 times to make it a 32-bit value.
This is done? This is the final version?
No, not yet. We are getting there. So this is what we have done so far. RS is fed to read register 1 so that the RS value comes out into the ALU. That's our first operation, our first operand. The next operand is going to be the sign extended immediate value, which is fed here. ALU is going to perform addition on it. In order to perform the addition, you need to tell the ALU that, hey, I want to add this value, not subtract it. So there will be a special control signal for the ALU, which has to be generated. We'll talk about that later. For now, we'll assume that immediate plus the RS value has come out in the form of an address. Since it is fed to the data memory, out comes the read data, and it is fed to the write data of the registers. Where do we want to write it? We want to write it into the RT register. And that's your complete load word hardware. So take a look into this hardware, see how the different lines have been connected. Yes.
The data memory module, write data part. Where would you use it, that one?
Where we would use that one if you want to write into the data memory. And which instruction do you use to write the data memory?
Yeah.
So
Well, yeah. So,
we'll talk about just after this.
oh yeah, I think so.
Yes, Marcos. Always 32 bits.
So read data 1 is 32 bits.
Yes. So RS is 5-bit address, but the value that is coming from that 5-bit address is going to be 32 bits, right? It's like think of RS, RT, RDS page numbers, right? If you have a book and I ask you to write 32-bit values on different pages, and if I ask you, hey, give me the value on the 4th page, it's going to be a 32-bit value. All right. Okay. Now here's what I would like for you to do. For the next 2 minutes, I want you to pair up, and the partner sitting to the left should explain the load word hardware to the partner sitting on the right. So pair up. So I guess Vijay, Amra, Jason, Clint. Yeah. RT is going to be your register that needs to be stored, right? So RT will go into the read register queue. It will come out of the read data queue and that will go into the right. Okay. Okie doke. So that's your load word. All right, jazz hands. That was your load word. Now the goal of the load word is to load a value from the memory into the register. Store word is the opposite. Store word stores the value to the memory address. So next, let's consider the store word operation. Now this is how the store word is going to work. We are still going to perform 24 plus $SP. So ALU is still going to compute the memory address. It is still going to compute that. However, RT this time will be read and that will be fed into the data memory, which seems to be missing. Where is it? Well, it is there. It is right there. So how would you modify this hardware now in order to perform the store word instruction? Do you think some rearrangements of different lines are required? If so, please discuss. How would you rearrange those lines? Yes. Yes.
So what I know that we have to use that data. Do you want to talk about that one or no? Which rows? RT?
Or we're going to shoot. So let's see what store word actually is.
From register to memory.
Yes, from register to memory. $S0, $24, RS, immediate RT, ALU result is equal to RS
I think it
plus
just goes
sign extended immediate, address. Data address is equal to ALU result. And then RT value goes to data memory. All right. Are we ready to discuss now what's going to happen? Now, this is your store word instruction. $S0, comma 24 $SP. Your $SP is still the RS register. It is still the RS register. 24 is still the immediate value. Your ALU still has to perform immediate, sign extended immediate plus the RS value. So RS will still go into read register 1 and out will come the RS value. Immediate will still be sign extended and it will go to the ALU second input. Out will come the target address where you would like to write to because it's a store word instruction. However, it is the RT value that has to be read and put into the right data memory, right? So this time we are going to read off of the RT register. We are not going to write into it. So these are the changes. Now, RT will go to the read register 2. RT will go to the read register 2. Out will come the RT value, and that is going into the right data port of the data memory. The address where you would like to write the data is RS plus sign extended immediate value. So he has specified where to write the address or which address to write to and what data to write.
And what is read data?
Read data in the end, well, technically that should not be there.
Okay.
That should not be there, and I'm going to remove it because that is irrelevant for the store word instruction. This is not needed for the store word instruction. Okay, so please have your attention on the board just one more time. Your ALU should still compute immediate plus RS, and therefore some of the things will stay the same. RS register address will go into the read register 1. Out will come the RS value. That's the first input of your ALU. The immediate 15 down to 0 will be sign extended to 32 bits. That will be the second input to the ALU. ALU will compute the target address where the data has to be written because we are using the store word instruction. What has to be written? Whatever is there in the RT register. So therefore, this time we have to read the RT register. So RT goes into read register 2 port. Out comes out of read data 2 the value of RT register, and that is going into the right data port of the data memory, successfully storing the value of the RT register. So that's the summary of the store word instruction. For the next 2 to 3 minutes, the partner sitting on the right should explain the store word instruction hardware to the partner sitting to the left. With the partner to the right is a little bit confused still, the partner to the left should help out. I'm glad. And this course will get you ready for hardware.
So one of my students, he's working for, now he's working for and he designed a control unit to control all of these different components for the MIPS process. So solid understanding of the data type is required. All right. So Gafur, you explained to Cairo. You're happy with the explanation? Okay. Kelvin, I promise you can be brutal and tell the truth.
No, I'm not.
All right. So the specific RC that's a great question.
Ben önce bu ara sıra sözün release yalnız değil. There's ara sıra same, right?
And then one is like I even get down
RC fire. Ben devam edeyim.
No, it didn't, but
RC was going to write it.
actually, yeah, I did. So
And yes, that is preserved whatever.
yeah, I did that. Well, I mean, it works for everything, but I was just seeing if you guys.
All right. Okay. Jazz hands one more time. Now, with the load word instruction, here's the deal. With the load word instruction, we had sent RT to write register. But for the store word instruction, we have sent RT to read register too. When it is an R type instruction, RD goes into the write register, right? So if you were to think of it, if you were to think about store word hardware and an R type instruction hardware, or even a load word hardware and a R type instruction hardware, you have RT and RD contending for the write register, right? Because for the load word instruction, RT has to go to the write register. For an R type instruction, RD has to go to the write register. So there's a contention, isn't it? How do you resolve that contention? How did we resolve contention between Ramesh and via multiplexer, right? So we will have such contentions. Are we clear about that contention though? So let's repeat this one more time here. You need to keep these conflicts in mind. One is going to deal with the register file conflict. When you consider the R type instruction, RD happens to be the register where the value has to be written. So RD has to go to the write register port for R type instructions, because R type is like RD is equal to RS plus RT. But for load word, RT has to be fetched to the write register port. So RT and RD, they're contending against each other for the write register port when you have a hardware that is both doing load word and R type hardware. For R type and store word instruction, RT is fed to read register 2. So you'll have to resolve those contentions using a multiplexer. Even your ALU has a problem. Even your ALU has a problem, specifically the second unit or second input. For R type, read data 2 is fed to the ALU, right? Because for an R type instruction, you are performing RS plus RT if it's a simple add. So ALU has to add the value of RS, which is coming out of read data 1, and add the value of RT, which is coming out of read data 2. But for load word and store word instruction, we are sending the immediate sign extended immediate value to the ALU. So the second input of the ALU, it has a contention there. And finally, when you're trying to write the data back, There's also contention. For R type, write data comes from the ALU, whereas for load word, write data should come from the data memory. Specifically, I'm talking about this port right here. For R type instruction, write data has to come from the ALU. But for load word, that has to come from the memory. So there's a contention there. So these are the three contentions that you have to resolve. You have three contentions. How many muxes would you need? 3 muxes. So please brainstorm with your peers and put muxes there to resolve this contention.
One which can give artifact and load word.
Load word is artifact.
Okay, merge artifact. Çatı yavaş yavaş. Yolda.
First, think about resolving the contention right here at the right register. The reason is for an R-type instruction, right register has to come from RD. But for the load word instruction, it has to come from RT. Let me repeat that one more time. For R-type instruction, right register should come from RD, but for load word instruction, it actually comes from RT. So here's the contention which has to be resolved. So how would you resolve it? There's a contention at the ALU now. Because between immediate and readers.
Right, they do, yeah.
I guess I can right type.
And the next one
Yeah.
I mean, like the line that you canceled with road back. Why?
which in
Yeah.
Yeah.
I mean, it's not really common that you like
That's like, if we're not scoring, basically, if we're not scoring, then
How much did you
we're scoring, we're not scoring three editing. Yeah. And if we are not, we're loading, then we use
Okay. This is too low for some people sitting over there, right?
Merge alt tab and load store would not open boxes.
So these are the three contentions. Contention 1, contention 1, contention 2, and contention 3. So you guys focus on contention 1. Okay. Contention 2. Right, result contention 2, okay? And actual result 2. You guys.
Bro.
Contention 1, think about it. Contention 2, you 3, think about contention 3.
Right?
Okay?
And
Think
one
about
more.
marks of contention 1.
Right.
You're on contention number 2.
Right here?
Uh,
Here, here.
So like about resolving contention number 3.
1, 2, 3. 3 boxes.
Lots of people say there's a contention that you might take of the resistance function.
Read there's a
In the
2
resistor file, there's a right data. There's a
to
contention
ALU.
there. Why? Because for load word instruction, right data has to come from the read data port of data memory. But for a normal R type instruction, that has to come from ALU results or the ALU. Right? So both of them are kind of
There's no
fighting
word
right
here.
data. How do you stop that fight?
So I guess for the
Yeah.
first one,
So, marks after the data proof.
And oh, this is and. Sorry. Yeah, that's my way of.
Okay, let's see.
All right. So my fellow computer architects, we have to get this done by 11:45. That's our deadline. So let's get this architecture out of our way. So who are looking into contention number 1? There's a contention at right register in the register file. There's a contention right here between RT and RD. So who were contention number 1? Okay. What about Manohar and Jasim? Where would you put the multiplexer?
for it's the registers for RT and RD. So maybe ones for RT and RD for Y register.
Okay, so right here?
Yeah.
Okay, so you mean to say something like this?
Yeah.
Okay, so contention number 1 is resolved. Very good. Contention number 2. Contention number 2 is at the ALU second input. Because for load word and store word, the second input will come as the sign extended immediate value, but for the R type instruction, it will come as the ALU. It will come from out of our read data 2. So who are looking into contention number 2? Okay, so Clint and team.
So we would put a plus between the sign extended and read data 2 going into the
Yes.
ALU.
Going into the ALU. You mean to say something like this,
Yeah.
right? Okay, so sign extended ALU, sign extended immediate value goes into this mux. Read data 2 goes into that mux. Contention resolved. Very good. So ALU conflict is resolved. Now we are looking at number 3 at the right data of the register file. Why? Because for load and store word, well, for the load word instruction, write data has to come from read data of the memory. But if it is a simple R type instruction, write data will come from the ALU. So these two lines are contending against each other. So Anna and team, where would you put the mux? Somewhere there?
Yeah.
Okay. What will be the two inputs? The ALU output and this line, right? The read data line. So were you visualizing something like this? Right? So there's a contention at write data between the ALU result and the read data. So to avoid those lines from clashing, we pass them through a multiplexer and then we feed it into the write data. Perfect. All right. I would let you take 1 minute to digest the solution. This solution right here, it determines how to merge the load word and store word hardware. And there's a glaringly missing line in my schematic. Let me fix it really quick. There you go. All is well with the world now. Please discuss this with your peers for the next 1 minute. Organize a little bit more. Okay. Okay. Yeah. Okay. But as you will see, next I'm going to have you look into that and that has to be some upstairs. Just so that the knowledge gets translated from here to there. Yeah. So the reason is, well, are we going back to the right place? But for load word, RT is the destination. All right. Okay. Now, here's what I would like for you to do. Please open up your laptops. Open up your laptops, open the Canvas. Under Canvas, under course overview, you'll find processor figures. And click at that link and please go over figure number 1. Partner number left, please explain it to partner on to the right. You're looking at figure number 1. So that's the fourth, processor figures is the fourth option under course overview. So you're looking at so this figure just does the load word, store word.
when you have between components, you will have input ports and you will have output ports. Programmers call it arguments, right? And the output are your return values.
This one would be the RT.
Hey.
Those are one app goes into
Yes.
same day, they are available. Same day. Yes. Oh, check all the data. Oh, some of those are. Some of them
As that's and I'll be just like this is the thing that we just did. Yeah, the basic idea is that
I think I know one.
correct.
Yes.
Yes.
That data.
It's a branch.
I thought it's what type is not.
Adding these two guys, you're gonna.
I guess it's the data. Level up. Shift edition. Okay. So much more than needed because it's
There are four. You see, right? Sure.
Zero.
You have 5 minutes to wrap up your discussion.
So the it looks like RT is always going to and then it's always going to be a register things.
Exactly. What is right now missing is telling the data memory whether to write it. That is the microcontroller. So yeah, so they will be controlled on data write. There will be a special line for data write. If it is set to 1, then whatever write data is specific here, it will make sense. Otherwise, it will not. But that's a very valid question. And that deals with control, designing the control unit. Control these So oh, sorry.
To which register file reports to others.
Well, that come from the control which we will design in our next class. So that's a very valid question. All of these boxes here, let's take that away. It requires a continuous read because this line is to write it as now the question is whether to write or not. That will be determined by the control. So it will generate a signal called write data. Right? If it is set to 1, then that means the write data makes sense. You're gonna have to write that data. If it is set to 0, that means that data is not is invalid and nothing has to work. Correct. Yeah. Very good. Calvin, I'm going to do the worksheet. You're not there yet. Don't rush. You have time for it. You have time. Yeah.
20 minutes.
All right. Okay, so I think 10 minutes are up and the time is 11:21. So that would leave you, I guess, with enough time not to discuss branching, but rather work on your worksheet. So please open up today's worksheet and you can work with your peers on that worksheet where you have to answer some interesting questions.
I have a question. Can I ask?
Just a second. Let me see assignments. Let's go to the worksheet first, right? And then we can ask the question. So if I were to see the student view, it's worksheet number 5, right? Worksheet number 5, and we are dealing with the add-I instruction. We are dealing with the add-I instruction. Now with the add-I instruction, you have first register, second register, followed by an immediate value. What my recommendation is, take a look into I-type encoding and find out whether these are RS, RT, or RD, and then answer these questions. Yes.
Yeah. So do we need to understand?
You know,
answer the questions. Okay.
Just the relevant part.
Okay. And the second one, basically, like. I can just like answer while looking on this, right?
Oh, you can.
Yeah.
Yeah. You're using that. You're referring to that.
What do you mean by the register?
This is register.
Register memory, register file.
Register 1, register like the data.
This entire series of register files.
Including
Import. So the wires that go in get input. You come out, those are out.
Which register file? Well, it says should go, but on the picture it already goes somewhere.
It already goes somewhere, yes. But yeah, for example,
RS is 0.
yeah, RT brings it to read register 2. But now the question is, should it also go here? Right. It depends on the add-I instruction, right? Yeah, exactly. You may work with your peers on worksheet number 5. Please look I-type encoding link on Canvas to find out RS, RT, and RD in these instructions.
Okay. In this case, RS will go to right register.
Yeah.
Huh?
Right.
Mhm.
So you say right there.
And first is the store. It's gonna store it there now. T0 RS.
What if you're done? Okay, if you're done,
RS is
then I would like for you to discuss about the branching instruction. Listen, now I can give you a brief insight into the branching instruction.
RS, o zebra button. Okay.
Your branching instruction is also an RI type instruction.
Okay, then. Invite register.
Those of you that are done, I would like for you to think about the branching instruction. So a branching instruction, for example, BEQ $S1 $S2, comma -48, let's say, right? This is our branching instruction. Now, this is how the branching actually works. When you consider branching, your program counter gets PC plus 4 plus sign extended immediate, which is multiplied by 4. That's what PC gets when you perform branch extension. So try to think about the hardware for this. If you're done with this worksheet.
It's also single cycle.
It is single cycle.
And then, so the -48 is gonna go to program counter.
There.
Major version.
Well, there's a reason why there's a random switching, and that is
So you wanna
to
have
allow for a little bit of randomness in this coding so that the hardware is simple. Well, now both hardware and software they go together, right? If your software is not amenable to the hardware will be too complicated. And if it is too complicated hardware, then something happens, and that is you cannot clock your hardware fast. And if you cannot clock your hardware fast, then your CPU is slow, right? Allow for a little bit of hardware freedom. You have to unfortunately sacrifice a little bit of programming.
All right.
Tiny more, software. Yes.
Yeah.
Right now.
Yes, it will answer.
No, but yeah.